We're going to do a little bit of drawing today as we learn about the molecular structure. Structure is important when it comes to developing new drugs and or new product. For example, understanding how atoms bond within molecules provides insight into cell replication. Building on this knowledge, the shapes of molecules reveal the effectiveness of important antibiotics such as penicillin. And scientists can manipulate shapes of these molecules to help design new cancer-treating drugs. So we're going to talk about the structure of ionic compounds and the structure of covalent molecules. The structure of an ionic compound, any ionic compound, is called a lattice structure. This is where positive cations are attracted to negative anions to form a network or a lattice of oppositely charged ions arranged in a 3D pattern. So you can imagine it goes negative, positive, negative, positive, negative, positive in a 3D structure where the negative represents the anions and the positive represents the cations. This lattice structure is for all ionic compounds. Now for covalent molecules, it's a little different. Now there is no one structure for all covalent molecules. You guys just explored all the different shapes of covalent molecules. The shapes come from a theory called valence shell electron pair repulsion theory, otherwise known as VSEPR. This theory states that electrons arrange themselves in a molecule so as to be as far apart as possible. Because think about it, electrons are negatively charged. What will two electrons do when they try to get close to each other? They will repel each other. So an electron will have as much space as it can get. Now a lone pair of electrons repels or takes up more room than a shared electron pair. Now remember when I say pair, it means two electrons, right? Two electrons in one pair. So when we talk about a shared pair of electrons, we're really talking about a bond. So how many electrons are in a bond? Two electrons are in a bond. Two different atoms are sharing each of their own electrons in a bond. A lone pair of electrons means that it is not sharing electrons with any other atom. It is not in a bond. It is two electrons on the central atom. So the VSEPR theory allows us to predict the shape of molecules in 3D. These are the different shapes that you guys just explored: linear, bent, trigonal planar, trigonal pyramidal, and tetrahedral. Couple things to note here. Take a look at the general formula. The general formula for a linear shape or a bent shape molecule will always have two outside atoms. So how is a bent molecule different from a linear shaped molecule? It's the lone pairs. A bent has a pair of lone pairs, or perhaps two pairs of lone pairs, whereas a linear shaped molecule does not have any lone pairs on its central atom. Now if you take a look at the linear shape, there are two different examples that I'm showing you here. One has two outside atoms with a central atom, again no lone pairs, while the other one has two outside atoms and no central atom. That is also a linear shaped molecule. Take a look at the trigonal planar and trigonal pyramidal general formula. How do we know that something is a trigonal shape? Because in the general formula, it's indicated with the 3. What does tri mean? It means 3. So here, how do you know the difference between a pyramid versus a planar shape? Well, the pyramid has a lone pair on its central atom, whereas a trigonal planar does not. Lastly, how do you know that something is a tetrahedral? Well, tetra means 4. The general formula, you see a 4 as a subscript, which indicates 4 outside atoms, and that is a tetrahedral. Now we draw Lewis dot structures to help us visualize how the atoms bond by sharing electrons. And by drawing the Lewis dot structures, it will also help to predict the shape of the molecule. Now remember, when we draw the Lewis dot structure, it's all about valence electrons. As a reminder, you have a picture of it on your screen here. So an example of a Lewis dot structure, now this one is actually very complicated, is down here. You see that a single bond has one dot pair where each electron is coming from the two different atoms. So one of these is from oxygen and another one of these are from hydrogen. There is a double bond where you have two dot pairs, and then you have a triple bond where you have three dot pairs. Now we won't draw Lewis dot structures that are this complicated just yet. We're going to start simple. In general, you want to always ask yourself, and this is how you check your work, are all atoms happy with 8 valence electrons? Remember that all atoms want 8, except for the really small ones, they're good with 2. So the exceptions here are hydrogen and boron. Hydrogen wants a maximum of 2 electrons, and boron wants a maximum of 6 electrons, not 8. In general, carbon, nitrogen, and sulfur can form double and triple bonds. So in terms of bonds, we have single, double, and triple bonds. And that's the highest it goes, to a triple bond. And you will learn later on in this video how these atoms form double and triple bonds. So let's take a look at CF4 and draw the Lewis dot diagram of CF4. First, you're going to count the total number of valence electrons. So using your periodic table, how many valence electrons does carbon have? We have 4 from carbon, and how about fluorine? We have 7 from fluorine, but there's 4 of them, right? So that's a total of 28. What's 28 plus 4? That's 32 valence electrons. That means that we have 32 valence electrons to work with as we draw our molecule. So, the first step is to put the single atom in the middle. So out of CF4, which one is the single atom? Carbon. So carbon goes in the middle. Now there are 4 fluorines. Now I like to keep my drawings neat, and I like to think about symmetry. So I put them around carbon in the order of left, right, bottom, top. It really doesn't matter what order you go in, just that you have 4 fluorines around carbon. And then we're going to draw bonds. Where do you draw these bonds? In between the 2 elements so that they connect, so that they are bonded together. So in each bond, we have an electron coming from carbon, and carbon has 4 valence electrons, so it makes sense that it has 4 valence electrons around it. And it's sharing with the 1 electron from fluorine. So 1 from that fluorine, another 1 from that fluorine, another 1 from that fluorine, and another 1 from that fluorine. Remember that each bond consists of 2 electrons that are being shared. So how many electrons did we just draw by drawing the 4 bonds? We drew 8 valence electrons. So from our total number of valence electrons, we're going to subtract 8. What's 32 minus 8? That's 24. Now we have 24 valence electrons to work with. So with those remaining valence electrons, we want to take care of the outside atoms first. How many more do you draw? If fluorine already has 2 electrons, then we're going to draw 6 more so that it has a total of 8. Remember, all atoms want 8 valence electrons, right? So let's draw 6 more valence electrons around each fluorine. Well, how many additional electrons did we just draw? 6 on each. 6 times 4 is 24. We drew 24 valence electrons, and we have none left. So let's double check our work. Does each element have 8 valence electrons? Yes, it does. Carbon has a total of 8. Remember that when it shares electrons in a bond, Fluorine's electron will count for carbon as well. And then each fluorine also has 8, 7 from fluorine, and 1 from carbon. So that's a total of 8. So we double checked our work and we're good. Every single element has 8 valence electrons. So what is the correct VSEPR shape of this molecule? We'll take a look at how many outside atoms it has. It has 1, 2, 3, 4. Do you remember the shape that indicates 4 outside atoms? That's right, tetrahedral. Now let's take a look at NH3. How many valence electrons from nitrogen? 5. How about from hydrogen? 1 each. So that's a total of 8 valence electrons that we have to work with. So the single element goes in the middle, and in this case that's nitrogen, and then you put your hydrogens all around it. So I do left, right, bottom. If you want to put your hydrogens on the top and the left and the bottom, that's fine. As long as you have 3 hydrogens, 1 nitrogen, and the correct number of valence electrons, that's all that matters. So now what do we do next? We put the elements down. Now it's time to bond them, right? So let's create the bonds. Let's keep count. How many valence electrons did we just draw? Yes, we drew 3 bonds, but remember that's a total of 6 electrons. So 8 minus 6 is 2. We have now 2 to work with. So where do we put the 2? 1 on each hydrogen? No, that wouldn't be right. Remember, how many electrons does hydrogen want? Hydrogen is happy with 2. Does hydrogen have those 2 valence electrons? Yes, it does. 1, 2. The 2 electrons that hydrogen wants are coming from that bond. One of the electrons are already hydrogens, and then nitrogen is sharing its electron. So each hydrogen already has 2 valence electrons. So if the outside atoms are good, where do you think those 2 leftover electrons are going to go? They're going to go on the central atom, and this is called a lone pair. So did we use up all the electrons? So 2 minus 2 is equal to 0. Yes, we did. So remember, we need to now double check. Does each hydrogen have 2 valence electrons? Yes, it does. Each of them are coming from the bond. What about nitrogen? Does nitrogen have 8 valence electrons? Yes, it does. 2 from this bond, 4 electrons, total of 4, total of 6, and a total of 8. Nitrogen has 8 valence electrons. So again, this here is called a lone pair. It's on the central atom. Now, if you're wondering if these electrons are also lone pairs, the ones around the fluorine, they're not lone pairs. What makes it a lone pair? The fact that it's on the central atom, okay? Not the outside atom. So this atom has 1 lone pair of electrons. So what shape is it? Well, taking a look at the outside atoms, we have 1, 2, 3 outside atoms. So it's got to be one of the tris. But which one? It's the pyramid. Why? Because it's the pyramid that has the lone pairs. Go ahead and try BF3 on your own. Keep in mind that boron also has an exception. It doesn't want 8 valence electrons. Instead, it's happy with 6. So go ahead and try this problem and play when you're ready to check your answer. So does your molecule match my molecule? You should have started with 24 valence electrons. After drawing 3 bonds, you subtract 6, so you have a total of 18 to work with. Remember, where do those 18 go? They need to first go on the outside atom. After you draw them on the outside atoms, you drew all of 18, so now you have none left. Are all of them satisfied with 8 valence electrons, and with the exception of boron wanting 6? Yes. Again, if your drawing looks a little bit different, where your fluorine is on top instead of on the right side, that's okay. So what shape is this? It's a trigonal planar shape because it doesn't have any lone pairs. Go ahead and try HF. Play the video when you're ready to check your answer. Did you get this far? I'm not done with my drawing yet, because I wanted to explain where these 6 valence electrons go. In this case, these are both considered the outside atoms. So then where would you place the 6 valence electrons? Would you split it up and put 3 and 3 on both? No. Remember that hydrogen only wants 2 max, and hydrogen has those 2 electrons coming from the bond. So with that said, where do the 6 valence electrons go? It's going to go around the fluorine. Now in this case, there's only 2 outside atoms, so you probably narrowed it down to it being linear or bent. And you're thinking, hey, aren't those lone pairs on the fluorine? Well, no, they're not. Because if these are both outside atoms, there's no central atom. So if there's no central atom, that means these are not lone pairs. Remember that lone pairs are only on the central atom. So this one is a linear shape. Go ahead and count out the total number of valence electrons for CO2. So for CO2, we have a total of 16 valence electrons to work with. I placed the C in the middle and 2 of the oxygens on the outside, and I used up 4 electrons, so that's a total of 12 valence electrons that are left. Where are those 12 going to go? Right, it's going to go on the outside atoms. So 6 on that O and 6 on this O. I used up all 12. Now I have to double check my work. Do all of the atoms have 8 valence electrons? If you take a look at this oxygen, it does have a total of 8. If you take a look at this oxygen, it has a total of 8. What about this carbon? Carbon only has 4 valence electrons. It doesn't have enough. It wants a total of 8. But do we have any more valence electrons to draw? We don't have any. We ran out. So what do? Well, in this case, now the oxygen is going to share more of its electrons with carbon. And guess what? That's how we get a double bond. So these electrons are going to share and form that double bond. Once it does that, these electrons are going to be erased because these electrons are now in the bond. Let's count it again. Now that we moved a pair of electrons, do we have a total of 8? Does this oxygen still have 8? Yes, it does. 2, 4, 6, 8. This oxygen is good to go. This oxygen is still good to go. We did not do anything to that. But what about the carbon? Does it now have 8? Well, no. It has 2, 4, 6. So what are we going to do now? If you thought that the other oxygen will now give up those 2 electrons, you're right. This oxygen on the right won't give up more electrons. It can, but remember I talked about symmetry? Let's just balance it out. So if we did it to this oxygen, then the other oxygen will share its electrons. And then we erase those 2 electrons. So now let's count it again. Does this oxygen have 8? Yes, it does. Does this carbon have 8 electrons? Yes, it does. 2, 4, 6, 8. Does this atom have 8 electrons? Yes, it does. So this carbon has 2 pairs of double bonds. Double bond on the left side, double bond on the right side. So what shape is this? Well, the bonds don't change the shape. We're still looking at the outside atoms, and we have 2 outside atoms with a central atom. So what shape is that? That's a linear shape. Let's take a look at our last example. Go ahead and try to do this on your own. So we have a total of 10 valence electrons. We just drew a bond, so that we subtracted 2 valence electrons for a total of 8. Those 8 are going to go on the outside of nitrogen. And it doesn't matter where you put those 8 valence electrons, because remember, these are both on the outside. So I subtract 8, I don't have any more to work with. So now what? Because if you take a look, the nitrogen on the right side does not have 8 valence electrons. So what did we say in the previous problem? We said that one of the atoms will share more of its electrons. Well, which one do you think will share its electrons? The one on the right or the one on the left? It's really going to be the one that has more electrons. So these are going to come in and share to form that double bond. So let's count again. Does it have 8 valence electrons now? Well, the one on the left has 8 valence electrons, but the one on the right? No, it has 2, 4, 6 valence electrons. So what now? Now, the one on the left will then share more of its electrons. And what do you think this is called now? Yeah, it's called the triple bond. Does each nitrogen have 8 valence electrons? Yes, it does. 2, 4, 6, 8. 2, 4, 6, 8. And we're done. What's the shape of this? There's only 2 elements here, right? 2 atoms, so they are considered the outside atoms. Are these dots considered lone pairs? No, because there is no central atom. So remember, if there's no central atom, they're not lone pairs. So what shape is this? Linear.